Hello, I'm Wenjie Xiong. In this video, I will share my work on leaking information through cache LRU states in commercial processors and secure caches. I will first give background on cache side and covert channel attacks, and then introduce our novel covert channel attacks using cache replacement states, showing our evaluation result on commercial processors. I will also show how our covert channel break the existing secure cache designs. Nowadays, many side channels and covert channels in processors have been used to break isolation and leak secret information. Many of these attacks are based on caches, with information leakage rate of up to 500 kilobits per second. One example is the recent spectral and meltdown attacks that exploit both speculative execution and cache covert channel attacks to leak information. Since these are hardware vulnerabilities, the fixes in software are very expensive. Also, preventing existing attacks is not sufficient, as new attacks emerge, such as covert channels through LRU state, as we will show today. Now let's look at what processor cache and how it can leak information. Cache is smaller and faster memory located on the processor core. It stores data so that future requests for the data can be served faster. For example, if I have an orange data block in the DRAM, if the processor core needs to fetch the data, it will fetch the data all the way through DRAM, causing long access latency. With cache, I can store the data on the cache so that when the core needs this data, it can fetch directly from cache, only needs short latency. This is called a cache hit. But if I have another data block that's not in the cache, we still need to fetch the data from DRAM. This is called a cache miss. This will cause long access latency. But overall, today's processor cache has very high performance that significantly reduces average memory access latency. But on the other hand, since there is time difference between hit and miss, the time information will leak the information. So how covert channel attack happen in cache? Cache is shared among different processes. For example, I have two processes, victim and attacker. The victim leaks information, so it's called sender, and the attacker will receive the information. There should be logical isolation between the sender and the receiver. However, if the victim has some secret dependent access, for example, if the access address depends on some secret, or there is some secret dependent branch that whether access one address will depend on the secret, such access will trigger cache replacement and thus change the cache state. For example, here the victim's access will trigger a cache replacement that replaces the orange block in this case. And then the attacker can observe the state change to learn the victim's access pattern. For example, in this case, attacker can access the orange block to see whether the orange block is in the cache or not to learn the victim's access pattern. Such attack has been shown to able to leak cryptographic keys in encryption and decryption algorithms, or leak victims' private memory in spectral and meltdown attacks. In our paper, we leverage an extra state called the cache replacement state, which is a metadata state in the cache. Why it's there? Because to fetch a new data block, an existing data block has to be evicted to make room for the new data block. And the replacement policy is needed to select an existing data block to evict. The most commonly used replacement policy is called the least recently used cache replacement policy. It requires a metadata state to keep track of the access in the cache. And in such replacement policy, the least recently used data block will be selected to be evicted. Now let's see how this will lead to a covert channel attack. Again, in this case, the cache is shared between the victim and attacker. and there is an extra LRU state in the cache. Overall, there are 3 steps. First, the receiver initializes the LRU state to a state known to the attacker, and then the victim has some secret dependent access, which will update the LRU state, which then observed by the receiver to extract victim's access pattern. However, to observe the LRU state is not trivial, because this state is not directly accessible from software. So in this paper, I propose to let the attacker first trigger a cache replacement, and this replacement will have an eviction depending on the LRU state. And then the attacker have a second access, which also measures the timing to determine what the state in the cache. Now let's look at a detailed example of how a covered channel works. Here I show 2 states in the cache, the set, which shows which edges are in the cache. I use numbers to show different edges that are in the cache. And the yellow row shows the LRU state. I use different black numbers to show the age of the edges, with 3 being the least recently accessed cache line and 0 being the most recently accessed cache line. And I show the 2 cases when sender have different behaviors, sending 1 or 0. In the end, for the 2 cases, the receiver will have different observation, even though throughout the attack, the receiver have the exact same behavior. And I also assume the address 4 is already in the cache. This is not required by the attack. I give this in the example to show our attack is different from other cache side channel attacks. So in the first step, the receiver sets the initial LRU state by accessing data block 0 and 1. The receiver accesses 0 and 1, and cache line 1 will be the most recently cache line in the cache right now. Then in the second step, the sender accesses data block 4 or not depending on the information to be sent. If the sender is sending bit 1, the sender accesses data block 4. This will trigger an update on the LRU state. Now cache line 4 is the most recently accessed data block. On the other case, sending 0, the sender do not access the cache and the LRU state remain the same. What we see here is cache miss is not necessary by the sender, and which data block are in the set remains the same in that step, but only the LRU state is updated. Then, in the third step, the receiver first accesses data block 2 and 3 to trigger a potential replacement. Let's first look at the left side. The receiver first accesses data block 2, which will fetch the data block 2 to the set and update the LRU state. Then the receiver accesses data block 3, but by this time, the cache set is full, so one of the data blocks should be evicted to fetch the data block 3. And we find, looking at the LRU state, cache line 0 is the least recent use line and will be selected by the replacement policy to be evicted. And then we fetch data block 3 into the cache. Then we update the LRU state. If we look at the right side, the receiver does the same. First access data block 2, which will fetch data block 2 into the cache set, and we update the LRU state. And then the receiver also accesses data block 3. At this time, cache set is full. We need to evict 1 cache block. And we find now that cache line 4 is the least recently used cache line and will be evicted and replaced with the new data block 3. Then we update the LRU state. In the end, the receiver measures the timing of access data block 0. On the left side, the receiver will find the 0 is not in the cache, observe a cache miss, showing a longer access latency. And on the right, the receiver will find a cache hit of data block 0, need only short access latency. So when the sender is sending different bit, the receiver will observe different access latency of cache block 0. Thus, the receiver can observe sender's access pattern. In this paper, we propose two protocols for covered channels in the LRU cache replacement state when the sender or receiver share memory or do not share memory, which I just showed an example in the last few slides. In this paper, we show the first demonstration of such covered channel in cache replacement state on commercial processors. So here is the receiver's observation trace from one Intel processors. When the sender and receiver share memory, we can see here the blue dot is the latency observed by the receiver. When the sender is sending different bits, the receiver will observe different latency. Similarly, we evaluate another protocol and show similar results. We also evaluate the error rate on the covered channel versus transmission rate. We find that in most cases, the error rate of the channel is less than 5%, and we conclude that this channel has an information leakage rate of up to 600 kilobits per second. In addition to evaluate the hyper-threaded case on Intel processors, we also evaluate the time sliced setting. Due to the frequency of context switch, the bandwidth is lower. We also evaluate such covered channel on AMD processors. It still works there, but due to the coarse-grained timestamp counter, it has lower bandwidth. Also, there is an extra micro-tag in the AMD L1 cache for linear edges, which make this attack a bit harder, but still break the AMD processors. Now let's look at how this covered channel will attack some of the existing secure cache designs. Let's first review what the previous cache side and covered channel looks like. First, the attacker changes the cache state by causing a cache replacement. And then attacker observes which cache line are in the cache to leak information. In this case, the sender must have a cache miss. And many of the existing defenses and also detection schemes leverage this fact that the sender needs a cache miss, either prevent the miss from happening or counting the miss to detect such attack. But in our LRU covered channel attack, we leverage the LRU cache replacement state. In our attack, the victim updates the LRU state and then observed by the attacker. And this state are updated on both cache hits and miss, which means cache miss is not necessary by the sender. Thus, the covered channel in the LRU state can still attack many of the defense schemes. There are a bunch of secure cache designs in prior work. There are two main solutions. First, cache partitioning, which provides stronger isolation between processes. Second, randomization, which randomizes victims' access and the cache state to decouple the access pattern and the cache state that cannot be observed by the receiver. Partition lock cache is one example of partition cache. The idea is to lock data block into the cache. Once a data block is locked, the block will not be evicted by any cache replacement until unlocked, such that the victim's new access will not trigger cache replacement. But the LRU state will still be updated by the victim. Thus, using LRU state, there could be still information leakage. In our work, we test the LRU covered channel attack in the PL cache in Gym 5, which is a microarchitecture simulator. Not surprisingly, we can retrieve the secret by observing latency from the attacker. To mitigate such attack, we change the PL cache design to also lock the LRU state. And after that, we mitigate the attack. The takeaway here is Partition Cache is only secure against cover channel attacks if the replacement state is also partitioned. We also look at one example of randomized cache, the random field cache. The idea is to decouple the cache state and access pattern. When one data block is accessed, the data block will not fetch into the cache, but another random address will be fetched into the cache. However, once the cache line is already in the cache, ith cache just behaves as a normal set associative cache. Thus, the LRU cover channel still exists in such secure cache design. And we evaluate our attack in the simulator and find the attack can work. We further qualitatively analyze the effectiveness of the cover channel in existing secure cache designs. We find that not all secure cache designs are secure against our cover channel because we use a new state in the cache. For partition cache, it must partition both eviction and all the access, and only if the replacement state is partitioned, it's secure. For randomize, it depends on where the randomization applies. If it applies for cache fetch, like in the random field cache, it's not secure. In conclusion, in this paper, we propose two protocols for novel cover channels in the least recently used cache replacement state, when the sender and receiver are shared memory or do not share memory. We also demonstrate this cover channel on commercial processors on both Intel and AMD processors, showing an information leakage rate of up to 600 kilobits per second. And we show this attack works even when the sender only having caching hits, making it faster and stealthier. Specifically, in simulation, we show this attack break existing secure cache designs such as partition locked cache and random field cache. We further qualitatively analyze the effectiveness of the cover channel in existing secure cache designs. We open source our attack code on our lab website. If you have any questions, feel free to email me. Thank you.